Hello everyone, am I audible? And my voice is clear and loud also. Is it? Okay, so we are going to discuss week 6 in this session, and tomorrow's session will discuss week 7, and Saturday we'll discuss solve with this both weeks 6 and 7. Okay, and so this is an open session of week 6. First of all, uh, how was the pitch? Is it fine to all of you? Any feedback? Anything? Want to say something? Good, bad, any ambiguity or anything? Am I audible? Julian is very silent.
About quiz, it was.
Okay,
Question was about
wait,
quiz.
just a second. Yeah, Vijay. Yes, I hope now I'm able to hear all of you. So yeah, Fatima saying something. Yes.
What was the question, sir?
Question was how was the quiz? Is it fine?
Quiz, yeah.
Uh,
It was, but we were not getting the answers as expected. Kind of, we were stuck in the calculations.
okay. So straightforward questions are there, direct questions. Like just know you know the concepts, you did some practice, and you got numeric is there. Okay, so let's start the session now. So in week 6, yeah, okay, something. Okay. In week 6, we are going to see two things. The first thing is the SVD, and the second thing is positive definiteness positive definiteness or positive definite. When we'll say a matrix is positive definiteness or a function is a positive definite, these two concepts are there in week 6. Okay, and so what is the SVD? So SVD is very simple, as we have a square matrix and using the eigenvectors we use to convert in means in diagonalization form, mean to say If matrix is diagonalizable, then we are able to write this matrix as a P DP inverse or S something whatever. In this fashion, we can write if the matrix is diagonalizable. So this is so why we are doing this? This will make us simple calculations. We are able to do on matrix. We are able to do some calculation in a simple way, like simply. If you want to find the power of matrix, you know, then this will make us easier to find the power matrix. So this is for a square matrix we did. So both are n cross n. But till now, so if suppose we have this one, suppose we have a rectangular matrix. Okay, so suppose a matrix of m cross n order, which is a rectangular matrix. So suppose some operations we want to do on the rectangular matrix. Is there any, so same question would be there as we here easily we can find some simple form there we can do other operations easily. So is there any form for the rectangular matrix also, so that we can do some operations easily here also in rectangular matrix? So this is the question. So because of this purpose, SVD is came now. Singular value decomposition, as the name is there. Decomposer. We are decomposing this matrix. So as here, this is a kind of decomposition. This one is a kind of decomposition. We are decomposing this. So here, so if it is a rectangular matrix, can we decompose this matrix in different form? Okay. Am I audible? Am I audible?
Yes, yes.
So to decompose it, how we can decompose? So this SVD, suppose we have a matrix of M cross N. Okay, so if we can write this matrix as a Q1, some sigma Q2 transpose. Okay, where Q1 is of order. This is going to be M cross N. Okay, this is going, and this is a matrix. This is going to be M cross N, whatever the order of matrix, this is going to be the same. Okay, and this is going to be N cross N. We have three matrices. First one is Q1, second one is sigma, and third one is Q2. And first one is going to be, of order M cross N. Second one is going to be M cross N, and the third one is going to be N cross N. You can easily remember this order. The reason is if you check this is M here, and you have to be sure that this is going to be a square matrix. Okay, this is also going to be a square matrix. So this is, if you remember, the or multiplication of matrices. So these two makes the order of the matrix, these two last. So using this two, you can easily tell the order of matrix Q1, the order of matrix Q2, and the M we can remember as the same order as the matrix have. So by this way, you can remember the order. No need to even remember. This tells you, and this is how it is. So this form is writing the matrix in this fashion. Okay, is called singular value decomposition. We are decomposing this in three type of matrices. So the question is how we will get, how we can get this Q1. This is this Q2. Why or how? What is the problem? So this is true for any matrix. Okay, any matrix can be decomposed. Any matrix can be decomposed in this fashion. Here the problem was on the diagonalize BLT concept. Are we able to diagonalize or not? Then this was the issue. But this is for any matrix. Okay, this is true for any matrix. So can we? So how we can get this? The question is now how we can get this Q1, okay, and this Q2. How we can get this? So to prove, you can see from the lecture. Okay, here the steps are you want to find Q1. So Q1 you can by the method we have a matrix A, right? So I said Q1 is of M cross M. So if you have matrix A, okay, which is of M cross N order, if you multiply with transpose, which is the order going to be N cross N. If you multiply these two, so then it will be order of M cross N. See that the outer one will make the order M cross M. So if you multiply these two, you will get a symmetric matrix. Okay? This is going to be symmetric. Okay? And this is going to be symmetric matrix. So it is, you can easily find orthogonal eigenvectors for this matrix. Okay? So find the eigenvectors. Okay, once you find the eigenvectors, fill in the matrix. Suppose you have a 3, for the timing, whatever the eigenvectors you got, fill in here, column wise. Okay. Similarly, others if you have. So this matrix is going to be of order M cross M. Okay, and this is going to be our Q1. Okay, all of you are able to get it, what I am saying?
Yes, sir.
Okay, and I feel so. This we multiply these two matrices, okay, here, and to find Q2, the order of Q2 is N cross N. Okay. So again, back to our matrix A. Okay, this is of order M cross N. So if you multiply A transpose A, see that the order of A transpose is going to be N cross M. Okay, and A is of order and M cross M. If you multiply these two, you will get a matrix. Okay, you will get a matrix of order N cross M. So you got a matrix of order N cross N. So again, this is going to be a symmetric matrix. Okay, this is going to be a symmetric matrix. So once we again a symmetric matrix, it is eigenizable, or mean to say it have the eigenvalues, n eigenvalues, n eigenvalues, not only n orthogonal eigenvalues. So whatever the eigenvalues will get again, fill in the column wise, fill it as a column wise. So you will get some matrix. This one, this matrix is going to be our Q1, Q2. This is a Q2. This matrix is going to be Q. Okay. And now the question is, what about the sigma? What is going to be sigma now? So sigma you can get, the sigma is just find the eigenvalues. Okay. Just find the eigenvalues of A. Okay. Once you find the eigenvalues of A, find the square root of those all. Okay. Sorry. Eigenvalues of I. Sorry. I just missed that. Not eigenvalues of this. Eigenvalues of which matrix? If anyone has gone through the content, what we do there? Eigenvalues
A
of
transpose.
A transpose. We'll feel the eigenvalues. We'll find the whatever the eigenvectors we got. Suppose eigenvalues we have. These are. So the sigma is going to be the matrix of this kind. Okay.
So what will happen if the sigma is negative? Lambda?
So in the case of, so first of all, the eigenvalues are going to be always positive or negative.
It will be always positive.
Why?
So that's what I'm saying. It will be always positive. Otherwise, we cannot get lambda if it is negative.
Okay. Anyone? The eigenvalues. What we will say about the eigenvalues?
It could be negative or positive or negative because it's a scaling or shrinking. But in SVD, it is said that it has to be positive. That's the question the other person is asking. So, what if they are negative?
Mm. So what is in the lecture? What professor said? It is going to be always positive. Anyone?
Yes, it is. It is going to be always positive.
So okay, it is going to be always positive. And why it is positive? What is the reason? Did he said in the lecture? This could be zero also. In the zero case, so there is another method, no, to find the Q2. So to find the Q2, okay, we'll back to the negative one. There is another method to find the Q2. What is that method? We'll use, what is that method? What we will do? We'll do the 1 upon, this is called the singular values. These are the singular value. So to whatever the eigenvectors we got here, V1, okay, this V1 here for these matrices, okay, V1, V2, V1, V2, some eigenvectors we got of A transpose, A transpose, okay, of A transpose, which we are, this is our Q, right? Q1. Whatever the eigenvectors we got here, so to form Q2, what we will do? We, anyone? What is going to be the next step? Some formula is there. Anyone have remember that formula?
I think we should take A transpose multiply with the vector which you have identified in Q1, the eigenvector, divided by the sigma corresponding eigen values.
A transpose V,
Yeah,
right?
divided by sigma one.
Yeah, divided by sigma 1, which is sigma 1 is nothing but lambda 1. Sorry, root of lambda 1.
Right.
So sigma I is going to be root of lambda I. So this is, by this way we'll get the eigen. So sorry, by this way we'll get the some vector. Okay, some vector here. Some vector we'll get, and we'll use this vector to fill the one matrix which will our Q2. But sometime the problem is what is going to be in the case of when sigma, this lambda is negative. Lambda is zero even. So what is going to be in, what we will do in this case? Even another question is when lambda is negative. Okay. So let's see. We just give a minute. Let's see even there what this professor is saying. So see, this is the reason here, not reason. It is always going to be positive. And why it is positive? This is these two equations because of these two reasons. So we will not think about the negative one. This is always going to be positive. And the reason is these two things. Okay. So what is the first reason? If you do A transpose A, okay, and Xi, then Xi is going A. This is going to be just lambda. Okay. Uh, so this is, we can sit to there, and this is going to be lambda xi, and the outside is xi, and this is going to be lambda I since okay. So this is the modulus value is 1, or norm is 1. So this is just a lambda I. And the second thing is here. Okay, this is another thing is that this is 1 here. Again, we can do the transpose this. This is going to be the same. And if you transpose it, this is going to be here this, and yeah, see, whatever the lambda I we are getting here, this is always going to be, this is, these two are same. Okay. These two are, you can see these two are same, and here it is tells you the positive. That's why each time this lambda I always going to be 0 or positive. So no need to worry as to why it is when it is going to be negative. So it is always going to be positive or 0. So in case of 0, okay, in case of 0, we can follow this method. Okay, if we are getting in case of 0, then we can follow this previous method, whatever I said. I have to do this, find the A transpose and feel it that this is going to be our Q2. But if it is non-zero, always each lambda is non-zero the case. Okay, eigenvalues of A transpose, we are getting the only the positive eigenvalues. Okay, then in this case, what you will do, you'll find the eigenvectors here v1, okay, v2, and you will fill in the matrix. This is going to be our q1. Okay, you will fill v1, v2, and you will, this is our q1.
So
And
just
now
can
the
you
next
repeat,
step.
can you repeat once again? If the lambda is 0, what should be the action?
If the lambda is 0, then do by this method. Do the A transpose A, this method, this one.
But
Because
if
this
then
method will,
if A transpose A is a very big matrix, say it's 4 cross 4, then it will be very time consuming.
it
Say
is going to be.
sometime 2 cross 4 becomes 4 cross 4. If I take
Okay.
A transpose, it is 2 cross 2. And if I take
Mhm.
A transpose A, it becomes 4 cross 4. So the process become very tedious. So we'll have, 4 lambda values, and multiplying that such a big, matrix 4 cross 4, it will
Mhm.
take long time.
Mhm.
Usually the practice should be, we should take a smaller matrix which is shorter out of Q1 and Q2, and we should work. But only issue is that if the lambda becomes 0, there what should be the trick?
So then another method is, if it is tedious, so then work is, see, if it is larger, then the work is going to be
Yeah,
less.
are you getting
When,
are you getting my question, sir? Actually,
yes,
say
I am
there is
getting
a
it.
2 cross 4 matrix, and
Yes.
and subsequently, if you're getting a value 0 in finally A times A transpose, that's a 2 cross 2 matrix. And
Yes.
subsequently, if you're getting a 0, then you try the other way around. That
Mhm.
time the matrix become 4 cross 4. So they are
Mhm.
finding the eigenvalue. It's a bit tedious process.
So if you don't want to proceed with this, that A transpose A, then what we can do? Anyone can tell? Then in that case, what we can do?
Sir, could you please show that?
Sorry.
What was the question, sir?
The question is, if it is suppose 0, okay. So I said do by this method. Do the A transpose A, means separately find the eigenvectors of, first find the A transpose, which we'll use to find Q1, and then find the A transpose A, which we'll use to find the Q2. Eigenvector of this one will be filled in this Q1, and the eigenvectors of this will find in the Q2, and eigenvalues is as the same method. Eigenvalue, so sorry, this sigma is nothing but the root of eigenvalues of a a transpose. Okay, but suppose the question is, sum of the eigenvalues of this one, means the same here, this one or this one same, is 0. Okay, sum of the eigenvalues is 0. So in that case, I am saying, if sum of the eigenvalues is 0, in that case I am saying follow this method to find the q. But if you don't want to do this, okay, if you don't want to do this, then what is the next method? There is another method. What is that method? Anyone tell? Anyone can tell what is?
Eigenvalues of these two should be same, right?
No, this not going to be same.
A transpose and A transpose A are not same.
No, it is
Sir,
going to be till,
eigenvalues are
no,
same,
till
but
matching time it
two
is going to be
eigenvalues
same.
are same.
If it is till matching time, it is this one. Non-zero eigenvalues are going to be same. Non-zero eigenvalues are going to be same. Okay, if it is a 0, then some of them may be 0 and some of them have some other also. Okay, so
Okay, A and A transpose is of small, small size, and A transpose A is of big size. Then in the first one, I'm getting zeros. Then in the second, the other one, I could have additional few eigenvalues. Is what you're trying to say?
correct,
Okay.
correct. No, so the question is, suppose it have some 0 eigenvalues. Then problem is, say, so let me tell you, in that case, what you will do, if you don't want to proceed by this method, so it is already mentioned in the lecture that the method is told in the proof itself. What is that? It is said that, okay, the whole process is, first find A transpose, find the eigenvalues, okay, then find the eigenvectors, okay. Once you found the eigenvector, then suppose one of the eigenvalues is 0, okay, some of the eigenvalues is 0, then there is no issue, you will easily find q1 eigenvectors, you can feel, okay, and this will be our q1. To find now q2 is, the steps are to fill, to find the columns of q2 is that you will do the A transpose of eigenvalues of whatever this v1 v2 have, okay, and this is 1 upon sigma time, 1 upon sigma time lambda I. Okay, this is a lambda I. Whatever the columns, sorry, vectors you will get, you will use to find Q2. But one of the eigen, suppose some of them is 0, then you cannot do this one. 1 upon 0 you cannot. Then in that case, what you will do? You will find an orthonormal vector. Orthogonal or orthonormal vector. This is the orthogonal vector. Find the orthogonal vector. Okay. So for the 0 eigenvalue, in place of that, fill that one. Are you getting? See, there are different methods. There are three methods. So for the 0 eigenvalues, you will not able to get this value. Okay. So how you will fill that column, particular column? Because one by one, suppose you are able to find the for V1. Sorry, you are able to get this for, I'm column wise. I'm making it C1, C2, but for C3. Okay, or even no, in increasing order it will usually fail to till this one you are able to do. Okay, till this two. The third one is 0. This third one eigenvalue is 0 here, so it will be 0 here. You cannot do this. Then what is the process to do? The process is find the a vector which is orthogonal to these two. Find a vector, okay, let's say u, okay, which is orthogonal to these two, and fill that one in place of this one. So this is C1, this is C2, and this is going to be U. Okay, so there are three methods you can follow on the condition, whatever the conditions we have. Yes.
Sir, could you please explain last step again?
So last, okay. So let me make it again. Maybe many people are confusing it, get confused. So the process is I have matrix A which is of order n cross n. I want to write in the form of Q1, okay, sigma Q2 transpose. Okay. To find Q1, what we will do? We will do A transpose. Okay, and we'll find the eigenvalues. Let's say the order is even I am fixing here. Let's say this is 3 cross 2. Okay, this is 3 cross 2. So this is going to be of 3 cross 3. Okay, this is going to be 3 cross 3. And find the eigenvalues of it. The eigenvalues are going to be lambda 1, lambda 2. Okay, these two are non-zero, but third one is 0. Let's suppose this is 0. Okay, so easily, okay, and I can find the eigenvector v1, v2, and v3. Okay, I will find the eigenvector. So q1 will be form v1, v2, v3. So q1 is now formed. This is our q1. The next step is I have to find q2. So q2 is going to be, what is the steps to find q2? What we will do? We'll do the A transpose, okay, and then v1 and 1 upon sigma 1. Okay, you will get some, let's say u. Okay, similarly we will do sigma. Sigma 1 is nothing but 1 uh, root of lambda 1. Okay, root of lambda 1. Okay, this is our sigma 1. Okay, now I got u1. For sigma 2 A transpose v2, I will get u2. Okay, but what about the third one? If I will do third one, so I will get 0 because the one eigenvalue is 0 here. Okay, so 0. So I am not able to find the next u3. What is going to be u3? Okay, not able to get. And this u1, u2 actually will use to find q2. q2 is going to be u1, u2, but u3 are not able to find by this method. So what we will do? We will do, so the next step is you have u1 and u2. So find a orthogonal vector which is orthogonal to this u1, u2. So let's say this is our u3 now, orthogonal vector, and that is going to be filled here. Okay, and by this method we will find q.
So this U3 is orthogonal or orthonormal?
So I think you can check how it's depend on if it is these simply these two are going to be orthogonal. So how we no so orthonormal. So orthonormal because the steps are I just missed that you have to make it orthonormal.
Yeah, because you have to normalize all this unit.
Yeah, you have to normalize it. So here this you have to find the orthonormal. Okay, this is one method. In the case of zero,
Sir,
you can follow.
V1, V2, and V3 are iron vectors or iron values?
Eigenvectors.
Okay. Sir.
V1, V2, V3, these are the eigenvectors. No? Here it is. And these are the eigenvalues.
Okay. Sir.
Okay. So this is one step. So there are three things we have discussed. So this is one method. Okay. Okay. This is in the case of zero. And suppose the case is this is there is no zero. Okay, there is no zero. Then you can follow the same process. If it is not zero, then the third one is going to be uh, sigma 3 and A transpose V3, which will be V3, and you can place it here if it is non-zero. Okay. And the next step is uh, if you are fighting difficulty, okay, either you can follow this method, find the orthogonal, or you can do to find Q2. In the case of orthogonal, you don't want to proceed by this method, so another method is find the A transpose A, okay, whatever the matrix you will get, and find the eigenvalues. Let's say eigenvalues we are getting some lambda 1 prime, lambda 2 prime, okay. So this is if we are assuming of 3 cross 2, no? So this is going to be 2 cross 2. So find the eigenvalues, then find the eigenvector. Let's say this is V1 prime, this is V2 prime, and Q2 is going to be V1 prime, V2 prime. This is our Q3. Okay. By this method, you can follow. Yeah, anyhow, normalize it. Both just normalize. Okay. So these are the steps you can follow to find the SVT. Okay. Is it clear? All of you?
Yes,
So
sir.
which will be the quicker method? So finding an
It's
orthogonal.
so with the method I will suggest you just do practice, you will get the idea.
Okay.
Best thing is because how I can tell. Just a second. Okay, let's quickly do the positive definiteness. Okay. So what is a positive definiteness? So simple steps is there. Suppose we'll think about only of this case of ax square plus 2bxy plus cx square. Suppose you have a, so we'll get the idea from here only. So suppose you have a this function. Okay. So this function, we'll say this function is positive definite when there is two definition, not two definition, there is two condition. We'll call this function as a positive definite when it is will pass through origin, means the graph of the function. Okay, if you suppose that if I will able to graph it, this is let's say x, y, and z. Z is going to be this is f of x, y. Okay, so this should be follow like this. Okay, means it should pass through origin. The first condition is this one, and the second condition is except 0, all values are going to positive. So if you write it is 0, 0 belongs to, okay, or maybe f of, there is going to be some x prime, y prime, which have 0, 0. Okay, and the second condition is f of x, y is going to be always positive. Okay, for any point. So if these two conditions are going to be true, then it is going, we can call this function as a positive definite. That's all the definition. And why we want this? Because there is one reason. Okay. The reason is this function, okay, this function we can convert, see, as the linear transformation. Okay, if you have a linear transformation, okay, which is kind of x plus y, something is there, we can find the matrix representation, right? Some matrix represented. This is a linear, so this is a quadratic. So we are not going to follow this method here as we did, but this will represent a matrix. A matrix, not only the matrix, symmetric matrix, square matrix, and the matrix is going to be this A, B, B, and C. See the coefficients here. Okay? Because of this reason, we are studying this type of function. Okay, and if this function is positive definite, no, so this matrix is also called a positive definite matrix. And the reason is why we call this as a positive definiteness, because if you calculate the eigenvalues of this matrix, let's say lambda 1 and lambda 2 it have, so both are going to be strictly positive. Okay. See the how it is connected. From this function we connected a linear a matrix, and matrix have this eigenvalues, positive eigenvalues. See how it is connected now. Okay. So this is the definition of positive definiteness. Okay.
Sir, could you please give an example?
So example is
That means that this AC should be greater than B square, isn't it?
so then the thing is that is the condition here. So,
AC must be greater than B square.
so here some condition we can now generate when it is going to be positive. So the positive thing is that, see, I said at each point this is going to be positive, means this is going to be positive at 1 0, at 0 1, okay, and some other point also. So if you check, if you substitute 1 0, you will get a is going to be 0. If you substitute it, you will just get, if you substitute here 1 0, you will get a only, which is, I am saying positive means a should be positive. If you substitute 0 1, you will get c only. That means c is going to be positive. And the next condition is, you can do the 1 1. If you substitute 1 1, then you will get something, some relation you will get, some other point, something that have substituted. Okay, but the condition is that not only these two will suffice us. The next is AC should be, no, what is that, AC should be greater than B square something. Yes, this should be the next third condition is, this should happen. If these three conditions simultaneously happening, then you can these three will also happen. Means either this is true, okay, either this is true, or if the coefficient having these properties, these three, then also we can say this function is positive. So this is a property for the function only. Okay. So example is, you can keep the example as, see, a is positive, so let's say x square, and ac should be greater than b square. So let's say ac plus 2xy, and you can see now fixed as a 4. So if we check, this is going to positive definite. See, the one is positive. Okay, C is positive. Now do AC. AC is going to be, no, it is let's say 6 even. Let's make it 6. So AC is going to be 6, and B square is going to be 4. So AC greater than B square. So this is a positive definite matrix. If I want to form this in matrix form, how I can form? See that this is 1 here, A is going to be 1 here, B is going to be what? 1 here. Okay. See, they are written out here. So 1, 1, and C is going to be 6. This is our matrix. If you check this eigenvalues, what is going to be the eigenvalues here? What is going to be the eigenvalues? Quickly, you can tell.
So 2xy, either of the, like someone should be 2, right?
Sorry.
In 2xy, either of
Hmm.
the b and d should be 2, right? 2 into 1 in your matrix form, all are ones and 1 6.
So here, see, if it is in this fashion, then we are writing BB, right? If it is 2B, then we are writing BB. So here, if it is 2 1, then 1 1 is going to be.
Okay.
Okay. Now, if we find the eigenvalue, so eigenvalue we can quickly find. This is going to be 6 minus 1, which is 5. And then fine, and here is trace is 7. So trace is 7 and eigenvalues is 5. How we can write in this fashion? There's something we can do. If you find this eigenvalues are, check. Can you check anyone that what is the eigenvalues here? Some difficult eigenvalues you get. Or let's do quickly. A minus lambda I. So this is 1 minus lambda. So 1 6 minus lambda. So if you multiply 1 minus lambda, 6 minus lambda, and minus 1 is equal to 0. So this is going to be 6 minus lambda minus 6 lambda plus 1 is equal to, sorry, minus 1 is equal to, sorry, minus 1 is equal to 0. So here is lambda 6 minus lambda minus 6 lambda plus lambda square also. Minus 1 is equal to 0. So this is lambda square minus 6 lambda, sorry, minus 7 lambda and plus 5 is equal to 0. So this is going to be b square minus 4ac upon 2a minus b plus minus upon 2a. So you can apply here, right? Square root formula. So this is minus b7 plus minus root square b square. This is going to be 49 minus 4ac. 4ac is going to be 20 upon 2a is just 2. So this is 7 plus minus 29 here and upon 2. So some positive and some negative things are happening. You can check. So here it is. Both are going. If we check, root square 29 is going to be something 4.5 something, no, 5.5 something. So see, it always going to be 5.5. So always it is going to be positive. This is always positive. So here that's See, we found the eigenvalues. This is always positive, or we can directly tell from here also, right? So this is the relation. Is it clear?
Yes, sir.
Okay, so this is a positive definiteness. The definition came from this function, but we have some broader case even. So the broader case is that suppose we have a matrix of order any size n cross n, but a square matrix. Okay, so we'll find the eigenvalues. Lambda 1, lambda 2, we'll find the eigenvalues. Okay, lambda n. If all are positive, then we'll call positive definite. This matrix is positive definite. Okay, if anyone is equal to 0, then positive semi definite. Okay, and the next is if anyone is negative. Okay, all are positive, anyone is negative. Anyone, not all, any of the or some of the, mean to say some of the positive and some of the negative. So better to write some of the positive, okay, and some of negative. In this case, you cannot decide definiteness, no, undefinite. So in this case, undefinite. But the next step is if all I is negative, strictly negative, then it is going to be negative definite. If each eigenvalue is negative, then it is negative definite. If this case is there, some of them is equal to 0 also, negative and 0, then negative semi, okay, semi-negative definite. So there are cases separately in set. So these are the cases we have. And that's all in week 6. Okay. This eigenvalues concept is clear.
Yes, sir.
So each time we'll follow the eigenvalues. We will find the eigenvalues, and according to that, we'll decide the matrix is positive definite, negative definite, positive semi-definite, negative semi-definite, or indefinite. So there are 5 cases. According to eigenvalues, we can decide. And the concept came from quadratic function. Okay, and the previous one was the SVD. Okay, anyone have any doubt?
From SBD, sir, how do you go for PCA?
There is no relation SVD and PCA.
There is no relation. But how to go from there?
PCA is different thing.
Okay.
PCA is totally different. Yeah, some you will see the similar notation there. You also will find the transpose some eigenvalues there, but that is totally different. Okay. So week 7 we'll see tomorrow. This is for week
Tomorrow, what time is the session? Tomorrow?
8 p.m.
Tomorrow 8 to 10, na?
Yeah.
Yeah, thank you.
Okay. Thanks, Steven. Thanks for joining.
Thank you, sir.
Okay.